the questions on this worksheet involve the same object, a 5 kilogram block of wood sitting on a flat table. I'm going to start by drawing a real basic free body diagram of that. So if you have a block, it's certainly going to have the earth pulling down on it, and that's the force of gravity. The table pushes up on it. We call that kind of force normal force. And since this thing is not in an elevator, it's not accelerating up or down, the forces have to be balanced in the up and down direction because it's at rest. And so that actually allows us to figure out what the normal force is equal to. It's equal to the force of gravity. We have a formula for the force of gravity. It's an easy mistake to make to say that force of gravity equals 9.8, but it doesn't. It's equal to mass times 9.8 if you're on the Earth. So we have a 5 kilogram mass. The gravitational field strength of the Earth is 9.8 newtons per kilogram. And so that gives us 49 newtons for the force of gravity acting on this block. And since normal force is balancing the force of gravity, the normal force is 49 newtons as well. That's important because the friction equation, and we have two of them, there's an equation to find maximum static friction, which looks like this, and there's an equation to find kinetic friction, which looks like this. Those friction equations involve normal force. And maybe a just quick note about the difference between maximum static friction and kinetic friction. So if an object is at rest, it experiences what we call static friction. The reason that we have a formula for maximum static friction is because when an object is at rest, the forces on it have to be balanced. And so friction has to simply balance whatever force someone is trying to push with. If someone pushes with a larger force, friction has to get larger to balance it out. If somebody pushes with a smaller force, friction has to get smaller to balance it out. So static friction can actually vary in how strong it is, but it has a maximum. There's a point where you push so hard that the object breaks free and begins to move. And so that's what we're calculating here. Another way I've seen this written, if it makes sense to you, is that static friction is always less than or equal to what you get when you use this equation. So it can be anything less than this number, and it can be equal to this number. But if it needs to be greater than that number, it can't do it, and the object breaks free and begins to move. Now, when an object moves, it experiences what we call kinetic friction, and that's what we would calculate with that formula right there. So I think it's a good idea to just calculate these values right at the beginning. So static friction, we're going to use the static friction coefficient that's given on this worksheet, and that is 0.5, which really means 50%, that the friction force is 0.5 or 50% of the normal force. So let me write this down. Fs max is equal to 0.5 times 49. It's equal to 24.5 newtons. That's just something we can refer back to as we solve these problems. Likewise, if I calculate kinetic friction, the only difference is that the given kinetic friction coefficient of friction is 0.3, which really means that kinetic friction is 30% of the normal force. That number ends up being 14.7 newtons. And this is typical that sliding friction, kinetic friction, is not as strong as the maximum static friction. Okay, with that background information, let's start answering some questions. So back to question number one. If we want to, it says in question number one that nothing is touching the block other than the table. So actually, this diagram that I've drawn here is a completely accurate diagram of question number one. There is no person trying to push it sideways. Therefore, it's not going to move. It's at rest. The forces in the sideways direction have to be balanced. There's no force that friction needs to balance. And so in this situation, in question number one, the force of friction would be equal to 0 because it doesn't need to balance anything. One of the questions is calculate or state the net force in the x direction. That's the same thing as the sum of the forces. This symbol right here is the symbol for net force or the sum of the forces. We're talking about just the x direction here. If we add up all the forces in the x direction, well, there's nothing to add. The answer is 0. The net force is 0 for question number 1. The other question is, what is the acceleration? Well, acceleration is equal to net force divided by mass. Since the net force in question number 1 is 0, that means that the acceleration in question number 1 is 0. Okay, let's go to question number 2. Question number 2, it says the block is initially at rest, but it's being pushed on with a horizontal force of 24.5 newtons. Let me draw that into my picture here. So now somebody is pushing with 24.5 newtons. And it says that it's initially at rest. The reason it says that is because we have to decide whether or not it's going to move. Is 24.5 newtons enough of a push to make it move? There is definitely going to be a backward friction force. The only question is, how big is it going to be? Is the friction force going to balance the 24.5 newtons and keep the object at rest? Or is the object going to slide, in which case the friction force would be simply equal to the kinetic friction force? So what you have to ask yourself is, well, how big does friction need to be to balance this 24.5? Well, it needs to be 24.5. So in order to prevent the object from moving, friction has to be equal to 24.5. Now the question is, can it be that big? Well, yes, that's why we calculated what maximum static friction is. Friction can be anything less than or equal to 24.5, and this is just the maximum that it can be equal to. So in question number 2, the force of friction is equal to 24.5. The forces are balanced, so when you add up the forces, you're going to get 0. Technically, anything backward is negative, so this is a negative force, this is a positive force. You add them together, you get 0. And of course, the acceleration then would be 0, because with a 0 net force divided by mass, you're going to get a 0 acceleration. Okay, let's take a look at question number 3. The only difference in question number 3 is that the person is pushing forward with a force of 20 newtons instead of 24.5. So if you let me get messy here, let me change this to 20 newtons. And for now then, let me cross off this. So here again, it says that the block is initially at rest. So you need to ask yourself, is 20 newtons enough to get this thing moving? How much force does friction need to exert to prevent it from moving? Well, it has to balance it. So friction has to be able to exert 20 newtons in order to prevent this from moving. Can friction exert 20 newtons? Sure, it can go anything up to 24.5. So now we know that this isn't moving. You're not pushing with enough force to make it move. You would have to push with more than 24.5, and you're not. This is not moving, so the forces have to be balanced. If something is not moving, the forces have to be balanced. Static friction is always equal to whatever it takes to balance the forces, as long as you're not going over its maximum. So the answers to question 3 are that friction is equal to 20. The forces are balanced, so the net force, the sum of the forces, is 0. Again, this is really a negative force here because it points to the left. The acceleration is 0 because we're taking a 0 net force and divided by mass, we're getting 0. So those are the answers to question number 3. Now, question number 4, things start to get a little different. Now, the person is pushing forward with 30 newtons. So again, I'll cross off this 20 and I'll make this a 30. Here again, it said that the block was initially at rest, so you have to ask yourself, okay, how much force would friction have to push with in order to prevent this thing from moving? So friction would have to push with a negative 30 newtons. The question is friction capable of doing that? And again, that's why we calculated this number right here. This is the maximum that static friction is capable of doing, 24.5. Well, this is bigger than that, so you know what? It can't do it. Static friction cannot balance this 30 Newton force. That's why we calculated this number. So now we know that 30 newtons is more than enough to get this thing moving. So we know that it is moving. And now things get a little bit easier. If it's moving, there's only one option for the force of friction. It's this that we calculated right here. Since we know it's moving, we know that friction is definitely equal to negative 14.7 newtons. So now we have to answer the net force question. And again, it's helpful to remember that this symbol can also be read as the sum of the forces in the x direction. Well, what are they? Negative 14.7 and positive 30. When you add those two numbers together, you get positive 15.3 newtons. So that is the answer to the net force. Then we can find the acceleration by doing, I wrote that wrong, sorry about that. All right, scribble that out. Try that again. Acceleration in the x direction is the net force, which is positive 15.3, divided by the mass, which is 5 kilograms. So you can pop that into your calculator. I think it's it is 3 something, 3.01 I think. Let's try that. 15.3 divided by 5. Oh, it's actually 3.06, positive 3.06 meters per second squared is the answer for the acceleration for question number 4. All right, moving on to question number 5. It says the block is moving at a speed of 5 meters per second, but it might be speeding up, slowing down, or staying constant. So that 5 meters per second is just the initial speed. And important, nothing is touching the block other than the table. I think I'm going to start this on a fresh piece of paper here and draw the free body diagram for this situation. Of course, we have the force of gravity, we have the normal force, and those are balanced. Let's assume that it's moving this way, and at least initially it's going 5 meters per second. I'm not drawing that on my free body diagram because you only draw forces on your free body diagram. Well, if it's moving this way, friction always points in the opposite direction of motion. So there's definitely a backward friction force acting on it. And in fact, since it says that it's moving, we don't even have to think about static friction. We can just say right away, oh, that's kinetic friction. That's negative 14.7. Now, what about a forward force? Well, it says that nothing is touching the object. If nothing is touching the object, then there's nothing that's exerting a forward force. That might seem confusing because it's moving forward, but what happened here is somewhere in the past that we don't really care about, something did have to push it forward to get it going, but then that something let go. And once it lets go, the object's going to keep moving for a while until friction makes it stop. And so right now there is nothing touching it, nothing that could be exerting a forward force on it. So there is no forward force. So when we have to answer a question like, what is friction equal to? Well, it's negative 14.7 newtons because it's sliding. What is the net force? If we add up the forces in the x direction, we get negative 14.7 because that's the only one. What is the acceleration? It's going to be the net force divided by the mass. And I think that's negative 2.96, but I don't remember. So 14.7 divided by 5, 2.94, negative 2.94 meters per second squared. The fact that that answer is negative matches the fact that it's moving in the positive direction, but the acceleration is negative. The acceleration is in the opposite direction. And when your acceleration is in the opposite direction of your velocity, you're going to slow down. And that's what makes sense here, that this thing would be slowing down. Taking a look at question number 6, it says the block is being pushed with a horizontal force that's causing the block to move at a constant speed. So again, let me draw the diagram on this one. Force of gravity, normal force, same as before. It says it is being pushed. That's an applied force, but we don't know what that is. It also says that it is moving, so we know that friction is kinetic friction, which is negative 14.7 newtons. The problem here is we don't know what that applied force is. So how are we going to figure that out? Well, what other information do we know? We know that it's moving at a constant speed. The important part about that is that its acceleration is 0. If something's moving at a constant speed, it has an acceleration of 0. That means that the forces have to be balanced. Therefore, the applied force is definitely equal to positive 14.7 newtons. Another way to figure that out is using our acceleration equals net force divided by mass equation. The acceleration is 0. This means add up the forces, so positive applied force, negative 14.7 divided by the mass, which is 5. If you solve this equation, you get applied force is equal to 14.7 newtons. So any way you look at it, the applied force is matching the force of friction, and that's why it's going at a constant velocity. So when you add up the forces, you get 0, and the acceleration is 0. Number 7 says the block is being pushed with an unknown horizontal force, and they say that it's accelerating and has an acceleration of 1 meter per second squared. So again, drawing a picture, force of gravity, normal force, balanced, it's definitely moving, so friction is definitely negative 14.7, but we don't know how big that applied force is. Since it does say that it's accelerating at positive 1 meter per second squared, I've drawn this force larger than that force. They're not balanced. The way we're going to have to solve this is, again, going to acceleration equals net force over mass. Acceleration is 1. This means add up the forces in the picture. We're talking about x direction here. So that's going to be applied force minus 14.7 divided by the mass of 5. To solve this, move the 5 over to this side. It cancels out there. We get 5 equals applied force minus 14.7. You're going to add this over to the other side, and that's going to give you an applied force of positive 19.7 newtons. That's the answer to the applied force. The friction force is negative 14.7. If you add up the forces, you get positive 19.7 minus 14.7. And that's 5 newtons. So the sum of the forces is 5 newtons. And of course, the acceleration is given as 1 meter per second squared. Last question gives us the situation where the object is slowing down and it has a deceleration of 4 meters per second squared. So again, drawing a diagram, force of gravity, normal force, it's definitely moving, so friction is definitely equal to negative 14.7. But again, we don't know what that applied force is equal to. I'm drawing it smaller than the force of friction because the object is slowing down. And so the acceleration is negative 4 meters per second squared. I'm assuming that the motion of the object is that way. Therefore, the acceleration would be in the opposite direction. So again, to find the applied force here, we're going to have to use net force divided by mass. Negative 4 equals the positive applied force, you can see that right there, minus the 14.7 divided by 5. This gives us negative 20 equals the applied force minus 14.7. And now, when you add 14.7 to both sides, you actually get an overall negative answer of negative 5.3 newtons. So what does that mean? Why do we have a negative there? It means that the applied force, I was wrong. It did not point forward. My math just told me that the applied force points backward. How is that possible? What does that mean? Well, it means that in order to make this thing slow down this quickly, in order to give it that much negative acceleration, you actually need to help friction to slow it down. You need to give friction a little bit of help to make it slow down. So what is the total force in the x direction? Well, it's negative 5.3 minus 14.7. It's negative 20 newtons. And what is the acceleration? Well, that's given.